Hello and welcome. In this video I'll be talking about arguments and truth tables. So to get a few words or vocabulary words out of the way, so an argument consists of two parts. There are statements that are called premises, and then the second part is a conclusion. We say that an argument is valid if the conclusion is true whenever the premises are assumed to be true. An argument that is not valid is said to be invalid, but oftentimes we'll say that that's a fallacy. So as far as testing an argument, one of the strategies that we can use here is to construct truth tables. And so the process for that is, usually we'll do it symbolically, and so as I've shown in some previous videos, we can use usually a lowercase letter to represent each simple statement in the argument. And then we can express each premise and the conclusion symbolically. And next we kind of combine the premises with conjunctions, and so that's what these little caret symbols are. So there may be two or three or however many premises there are, they would all be joined in an and statement. And then finally that compound statement becomes a part of a conditional statement, and we'll see if that leads to the conclusion. Finally, we'll take this entire compound statement and construct a truth table, and if the final column has all truths, then the conditional statement is a tautology, and we say that the argument is valid. Now, if we don't end up with all truths, so even if there's just one false in that final column, then it's an invalid argument. All right, so let's look at an example. So here I have a statement. If MARTA is not running, there will be traffic delays. There are no traffic delays, so MARTA is running. So there are some simple statements here that we should define. I'm going to use P and Q. For P, I'm saying that MARTA is not running. Now, I want to point out, you may choose to write this in the affirmative, MARTA is running, and later then you could negate that and say that not P for MARTA is not running. It's not going to make a difference in the end result. And then for Q, there are traffic delays. So the way this argument works, if MARTA is not running, there will be traffic delays. So that's our first premise. And so when we're writing this as an argument, that first is P, if P, then Q. If MARTA is not running, there are no traffic delays. So that's premise number one. And premise number two says there are no traffic delays. So Q says that there are, so this is not Q. So that's premise number two. And the conclusion is this last piece. So MARTA is running. This symbol of three dots that are in this kind of triangular formation, that is read therefore. And we use this to precede the conclusion in an argument, or to denote the conclusion. So therefore not P. So I need to combine the two premises in a conjunction. So that's what we see here. If P, then Q, and not Q. Now all of this, we're going to check to see if that implies not P, the conclusion. So we'll do that using a truth table. So let me just keep this partially visible. Here is our statement. If P, then Q, in conjunction with not Q, implies not P. So I start with P and Q, and my basic values true, true, false, false for P, and true, false for Q. I know that later on I'm going to need not P, and so I went ahead and added that as a first column here. So I just, this true becomes false, true becomes false, false, true, false, true. So, but the first piece of this argument that I need to analyze is the first premise. If P, then Q. So I'm focusing on just these values. remember that in a conditional statement is only going to be false when the antecedent is true and the consequent is false. So I have a false value here and it's true everywhere else. So that's just this one piece. Now I need to form a conjunction with not Q. So here I've added a column for not Q, and so my values are false, true, false, true. And then I can take that information to evaluate the conjunction. So I'm looking at these two columns. Now a conjunction is true only when both components are true. So I need two true statements. Well, I have a true and a false, so the conjunction is false. Here I have a false and a true, so the conjunction is false. And again, I have a true and a false, so a false. It's only in this last row that I have two true values, so the conjunction is true. Now finally, I take this entire statement and join it in a conditional statement with not P. So now here's where I need to look. Here's my antecedent, here's my consequent. Now, anytime the antecedent is false, the conditional statement is true. So I have a false, 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 I have true, true, true. Now, when the antecedent is true and the consequent is true, this is true. So the only time I would have an issue with the conditional is if I had a true antecedent with a false consequent, and that never happens. So I end up with all values of true here. So this is a tautology. So that is a valid argument. All right, let's look at another. In this one, we have, you must eat well or you will not be healthy. I put happy there first. I eat well, therefore I am happy. So here I've structured this where I have premise number 1, premise number 2, and the conclusion. And so the simple statements are, I eat well, I am healthy. And so in the first premise we have, you must eat well or. Now notice you can change these pronouns from you to I just wanted to be consistent and put it all in the first person. So this is the first premise is an or statement, it's a disjunction. And here I eat well, but this says I'm not healthy. So I wrote this symbolically as P or not Q. The second premise is I eat well, so that's just P, and the conclusion is I am healthy, so that's Q. So when we take our first premise and our second premise and we join them in a conjunction, this is the compound statement symbolically, and then that becomes the antecedent in a conditional statement, and we're going to check to see if that is true when Q is the consequent. So my two simple statements are P and Q, so I have my standard values of the truth table. True, true, false, false for P, and then alternating true, false for Q. I know I'm going to need the negation of Q, so I've added that here. False, true, so I've just switched the values for Q. Here I have the disjunction, P or not Q. So I'm looking at these two statements. In a disjunction, I just need one or the other to be true. So that happens here, here, but in this row, both are false, so the disjunction is false. And then I take that statement and form a conjunction with P. So now I'm looking here. Now a conjunction is true when both parts are true. So I have two trues, so this is true. Two trues, so this is true. Here I have two falses, and here I have a false and a true. So I have true, true, false, false. And now I need to see if this entire compound statement implies Q. So Q is here. So remember, in a conditional statement, it's going to be false whenever the antecedent is true and the consequent is false. So if this is true and this is false, I'll have a false under here. But here I have true, true, so this is true. Here's the case where I have a true, false. so that I get an F here, that means that this argument is invalid. I only need one false in this final column to invalidate the whole argument. So this is a fallacy. All right, so that is how we can use truth tables in argument analysis. I have one other video from this section on logic. I will look at one other strategy. I hope you'll for analyzing arguments. I'll see you then.